Okay, this is the 14.7 video. Let me just warn you, I am not making this in the morning. I'm making this in the evening, which means my family is home, my daughter is awake. There's probably going to be some interruptions, just heads up. But maybe they'll keep it to a minimum. We'll see. Who knows? All right, so 14.7 is more on triple integrals, but this time it's cylindrical and spherical coordinates. So cylindrical coordinates are just the three-dimensional version of polar coordinates, but spherical coordinates is something new. So we'll go a little more quickly through the cylindrical because we've already spent some time on the polar, and then we'll talk a little bit more in detail about the spherical. Okay, so they talk in here about how whenever you're doing something with cylinders, cones, or spheres, cylindrical or spherical coordinates can make your life a lot easier, just like polar coordinates made your life a lot easier when you were doing things where the region was a circle. So for cylindrical coordinates, notice what you have. This is, again, the three-dimensional version of polar, so you still have the r and theta like polar, but you have this extra z component that you didn't have before. So here's a picture of it. The theta goes from the positive x-axis toward the positive y-axis, just like it does in 2 dimensions, but it looks different now because it's laying down, so it looks a little different than normal. Like, let me show you on here. So in 2 dimensions, the theta was going that way from the positive x to the positive y. So it's still doing that here from the positive x-axis toward the positive y-axis, but it's just in a different place because of the fact that it's three-dimensional. So that's the theta. The r is still how far you go out along that ray. But then now you have the z component, which is how far you come either up off the xy plane or down below the xy plane, depending on whether z is positive or negative. So z is like the height, right? So you're going up or down depending on whether you're positive or negative. So down here they have the definition, and that's pretty much what we were just talking about. So here's the equations. These are the same equations that you've had before, except for this one is the only new one. Really going to be hard to memorize that one, but that's the one that's new. So that'll probably be the easiest formula you ever have to memorize. Okay, so here, I'm going to let you read this on your own. This is page 803. Please go back and read this. This is just kind of describing the situation. This is telling you when they would be helpful. And then we'll talk about some of this other stuff in my notes in just a second. But in cylindrical coordinates, on a triple integral, the dv, which normally would have been dx, dy, dz, or any of the other 5 possible combinations because there were 6 total. Now, see how here you have the r dr d theta like you had in polar, the r dr d theta from polar, but now you have the z. So I usually write it as r dz dr d theta. The book writes it as dz r dr d theta. It doesn't really matter. But here's what you have for the triple integral. D, remember, is the letter that they use for the region when it's in polar. R is if it's in rectangular, D is if it's in polar. I don't know why it's not P for polar, but I didn't write this book. So triple integral of the function, and then I'm going to do R dz dr d theta because that makes more sense to me, but that would be what it's going to look like in triple integrals. So they have, again, I'm not going to read this to you, but just to point out so you can look at it later, on page 804, how to integrate in cylindrical coordinates. Obviously start with the picture, find the z, find the r, find the theta, and then this is the formula for it. So again, d is the region in terms of polar. You have a function of r, theta, and z, and then the dv. So your outer bounds are going to be the bounds on the theta, and that's going to be typically, you know, radians like 0 to pi or something like that. R is going to be a function of theta, like maybe, you know, cosine theta or something like that. And then z is a function of r and theta. And then here again, the dv becomes r dz dr d theta. Okay, so that's your formula for a triple integral in cylindrical coordinates. So let me show you that in my notes, and then we'll move on to spherical. So the only thing that's in my notes that wasn't in your book is this little section here, and it was in your book, but it was kind of more in a paragraph form and more with a specific example instead of in general. So I think this is an easier way to look at it because it's in general. If you have r equals a number, in polar that used to be a circle, but now in cylindrical it's a cylinder because the z is free, so it's going to move up and down and make a cylinder out of that circle. Before theta equals a number used to be a line, but now because the z is free, the line's going to move up and down. That's going to make a plane. Z equals a number is always has been a plane parallel to the xy plane. And then r equals 0, that is the z-axis. It's the same thing as a cylinder radius 0. So r equals 0 is the same thing as a z-axis. So that part is not written exactly like that in your book, so you may want to write that down in your notes. But the rest of this stuff is in your book. And so you can see it from there. Here on this formula, this is the same formula that was in the book, but notice I couldn't fit it all. So all of this is the formula. And so this part of it's down here. So don't forget about that part down there. Okay, so that's cylindrical again, just like polar, but with an extra dimension in it. But now we're going to look at spherical. So this is page 806. So in spherical coordinates, what you have is you have rho, phi, and theta. So the theta in cylindrical and the theta in spherical are the same thing. They both represent the same thing. They're found the same way. So that's the same piece. But this rho and phi, that is new to spherical. So here, a little bit of an explanation. Here, a little bit of an explanation. So on page 806 again, go back and read this later on your own or pause the video and read it now. I'm not going to read that to you. Say hello to some crazy girls. One of those is my daughter. If you were able to see her through the window, I'm sure you could guess which one was her. She's the one that looks just like me. Okay. Anyway, here we go. Spherical coordinates. They're being silly. I can hear them. I told you that's going to be the first of probably many interruptions in this video. Okay, so spherical coordinates. Theta, same thing. Start at the positive x-axis. Move toward the positive y-axis. Rho is very similar to r in that it's how far you move out along the ray, but a big difference is rho can never be negative and r can. So that's the difference between rho and r, but they both represent distance from the origin. And then the phi, this is a new part too, it is starting at the positive z-axis and then you're falling toward the xy plane. So because you're falling, you can fall as far as from here down to the negative z-axis, and that would be pi. So phi can never, it rhymes, so that'll help you remember. Phi can never be bigger than pi. So phi is always between 0 and pi. I have this stuff written down in my notes in a second. I'll show it to you if that's easier, if you're not really verbal. I have that written down in a second. But so theta is how far you go around. Phi is how far you fall down. Rho is how far you go out. Okay, so that's how they are. They have them kind of summarized here for you, all three of them. Rho is distance. These are both angles. So phi, like theta, is going to be an angle measure, but again, the biggest it can ever be is pi. All right, now these are some new ones, and these are going to be hard to memorize, but these are the spherical coordinates. If you're, they have the connection with r from cylindrical, but they also have the connection with x and y from rectangular. Okay, so these are the formulas for switching back and forth between the coordinate systems. Okay, and then it tells you here on page 807 what spherical coordinates are useful for. So again, I'm going to let you read that on your own so you can look at that. But one thing that's important about spherical, just like, do you remember from polar and cylindrical, when you switch from either dA or dV over to polar, you have that r, that extra piece that pops up, the r. So spherical has the same extra piece that pops up, and it is rho squared sine phi. So the dV, when you change, instead of an r popping up like it does in polar or cylindrical, you have a rho squared sine phi that pops up. Okay, so that's just the extra piece that comes up. It comes from, you know, if you were doing like the polar rectangle kind of things, it's like a slice of a sphere. I don't know if that really makes sense, but anyway, that's where it comes from. And so that's the extra piece that you're going to have to put on every time you integrate. So again, you could read this later on your own, but on page 808, how to integrate in spherical coordinates, always start with the picture, then find the rho, then find the phi, then find the theta. So here's the formula in spherical. Again, the region D, they're using here to distinguish it from rectangular coordinates. This would be in spherical coordinates. And so I have no idea what that noise is. I'm sure that's my husband doing something. Okay, I don't know how many of these noises that you can hear. Probably not very many, since my microphone, you say it's hard to hear me, but there's all kinds of crazy noises going on today. So who knows? I'll mention them in case you can hear them, tell you what they are in case you're wondering, but maybe you can't hear them. Anyway, theta is the same thing as before. Phi is between two numbers, the smaller one and the larger one. I guess they kind of ran out of Greek letters to use here. I don't know why they did that, but anyway, rho is going to be a function of phi and theta. Here's your function in terms of rho, phi, and theta, and then that extra piece that pops up when you switch it over. So this is, again, just that extra piece that's going to come up every time, just like the r that pops up in the r d theta, and then your d's. Okay, so that's the formula for integrating in spherical coordinates. So they have a pretty nice summary here on page 810. This is not everything, but it's most of the stuff. So if you're working problems and you need to find them quickly, this is a good place to look. But let's look at my notes. So spherical, just in case it's easier, I wrote it out. This is rho, and this is phi. So kind of like high, and row like row your boat. That's how you pronounce them. Okay, so again, rho is always positive. Phi can not be any bigger than pi. Here's your formulas. And then here's some, this, I don't know if this is in your book. I mean, it is in terms of like in paragraph form or with an example, but I don't know if it's in there just like this. But if rho is a number, that's a sphere. If phi is a number, that's a cone. If theta is a number, it's still a plane, just like it was in cylindrical. And for the specific case of when phi is pi over 2, that, again, it tells you how far you're falling. So if you were at the z-axis and you were falling and you fell pi over 2, you'd be in the xy plane. So that would be the xy plane. So there's a couple special cases. Again, that stuff at the bottom is not necessarily in your notes in that form. All right, let's look at some examples. Because who does not like working calculus problems? Oh, just kidding. Before we do some examples, here's the formula. This was the same formula that's in your book. I just wanted to, again, remind you that this piece of it wouldn't fit because these are too long. So it's down here, so don't forget about that piece. But it's the same as what's in your book. All right, we're going to look at number 6. So the first group of problems, 1 through 6, it's already got it set up for you. All you're doing is integrating. So you don't have to change anything or draw anything. You're just integrating. So triple integral. Notice here the book, they put this r over here. It's not a big deal until you get ready to integrate with respect to r, but it does need to be part of this. So I just go ahead and distribute it because that r has to get distributed to this function. So I distribute the r and I get this. Now I'm going to integrate first with respect to z. So integrating with respect to z, just stick a z on the end of everything because it didn't have z's. Then you're plugging in. Here is my work for plugging in. Why is my phone? There we go. Simplify to here. Okay, so this is what you have after your first integral. Now you're going to integrate again, this time with respect to, well, this is actually 1 over 12. I just didn't simplify till the next step. But anyway, you're going to integrate with respect to r next. Okay, so integrating with respect to r, these already had r's on them, so you do have to integrate. But notice sine squared of theta is a constant with respect to r, so it's just kind of hanging out. So plug in and simplify. So it simplifies down to this, and now you're ready to integrate with respect to theta, but you cannot integrate sine squared. Do not write 1/3 sine cubed. So instead of integrating that, you rewrite it using this trig identity here. I'm going to clean it up a little bit, so distribute that 1/8, combine this piece, which is 1 over 24, which this piece, which is 3 over 24. You get this. I'll simplify it in the next step. Integrate with respect to theta, plug in. I guess my answer's on the next page. Yes, pi over 3. All right, sorry, I'm trying to adjust my papers. That's probably not the easiest thing for you to look at. So sorry. Okay, so let's try another problem. Next group of problems, different sets of directions. So we're here in the 7 through whatever. It says, blah, blah, blah. Evaluate the integrals in 7 through 10. So these are already set up for you. It looked like it was a different set of directions, but it deceived me. It is the same. Just integrate. So try this one by yourself. It's number 8. So here's number 8. Pause the video, try it by yourself, come back and see if you got it right. All right, so you should have gotten 12 over pi. In case you didn't get that, here's my work. Here, notice that it had it set up integrating with respect to r first. And so you have to integrate with respect to r first. Then you're plugging in. So after your first integral, you would have, well, you would have this, but then you have to do FOIL. So when you do FOIL, you have this. I skipped a step apparently. Sorry. This was cosine squared. So cosine squared, you can't integrate it, so you have to write it like this. So this came from cosine squared. I didn't show that step, but FOIL this out, and it's 1 plus 2 cosine theta plus cosine squared theta, and then this is what's cosine squared theta. Okay, so then work. It is this before you integrate. You can distribute that too or not. It probably would have been better because it would have gotten rid of some of my fractions, but I didn't distribute it. Integrate with respect to theta next. Plug in, and then you should be here. 6 pi. Integrate with respect to z. and then you get 2 pi. All right, so those are pretty straightforward if you can do double integrals. Let's move on to some that are a little more challenging and much more exciting. This, number 14, is in rectangular. So it wants me first to change it to cylindrical and then to evaluate it. All right, so here's what I have. And notice you have to change 3 things. You have to get your bounds in terms of cylindrical. You've got to get your function in terms of cylindrical. And you've got to get, this is your dv, you've got to get your dv piece in terms of cylindrical. So this is the same thing in cylindrical as r squared. This is the same thing as r dz dr d theta. Don't forget the extra r. So now let's work on our bounds. All right, this is what it looked like in rectangular. This is what they gave me. Remember, x is the same thing in cylindrical as r cosine theta. So z less than or equal to x becomes z less than or equal to r cosine theta. And then for this one, x equals this piece. If you work it down, that's just the unit circle. But then x was between 0 and the circle. Y was between -1 and 1, so it's the right half of the circle because the smallest x value was 0, so it's only just this right half. So in cylindrical, the z is between 0 and r cosine theta. Again, that came from the x. The r is between 0 and 1. And then the theta, it's from here to here. So negative pi over 2 to pi over 2. So set it up this way. This is my r squared, which came from the function here. And then this is my r, which came from the dv. So together that makes r cubed. Integrate with respect to z, plug in, simplify. Integrate with respect to r, plug in, simplify. Integrate with respect to theta, plug in, simplify. All right, so that is number 14. So switching from rectangular to cylindrical is pretty straightforward. It helps to draw the picture, the r, and obviously it helps to have the formulas memorized. All right, let's try the next one. Here's the directions. 15 to 20. Set up the integral, and notice this is in cylindrical. So here they just give you the information in the picture. We're going to look at 16. So here's the picture. I drew it in my notes, but it looks way better in the book, obviously, because I am not an artist. But there's the picture. So I have a cylinder, hence cylindrical coordinates. All right, let's look at it here in minutes. Okay, so here's the picture. And here's what I have. Notice this is not in cylindrical, so that's got to be fixed. That's not in cylindrical. You have to put it in cylindrical. So x, remember, is r cosine theta. So in cylindrical, it looks like this. And then here's my picture. So the 2D, goodness, can you hear my daughter screaming? The 2D projection is in the xy plane. And notice the y is always positive because it stays in front of the yz plane. But the x can be, sorry, I said that wrong. The x is always positive because it stays in front of the yz plane. But the y can be positive or negative. So it's this circle here. And it just comes from, again, the floor, basically, of this cylinder. Okay, so your z stays between 0, which would be the xy plane, and the 5 minus x, which we changed to cylindrical. The r, it told me up here what that was, so that's where I got that from. That gave that to me. Thank you very much. And then looking at my picture, I have negative pi over 2 around to pi over 2 for my theta. So here they didn't give me my function, my f, so I can't actually integrate this. So I'm just setting it up. But what you want to do is on your f, make sure to use r, theta, and z. Do not use x, y, and z because that would be rectangular. And then don't forget about your r, dz, dr, d theta. All right, let's see what's next. 22. Ugh, a stupid tablecloth. Okay, what are the directions? Here we go. Now we're moving on to spherical. Evaluate the integrals. They're already set up for us. We don't have to do anything but integrate. So if you want to try this one on your own, it's just a basic triple integral, different letters, but the approach is still the same. So try this one by yourself. Pause the video, try it by yourself. All right, so check your answer and then I'll show you the work. Come on, cooperate with me. 2 pi. 2 pi is the answer. Okay, so let's look at the work just in case. So notice here you had a row squared. Here you had a row. It's row cubed. Integrate with respect to row first. Plug in and simplify. Then notice this needs a u substitution. I chose my u to be sine just so I didn't have to deal with the negative. If you chose your u to be cosine, this would work also, but you'd have to deal with the negative. So I chose it to be sine. Simplify down to here. I kept forgetting my d theta, so I just kind of had to squeeze it in. That's why this is so messy. And then apparently I lost my 4 too. Whatever, whiteout is my best friend because, you know, I use it all the time. So we really get along well. Okay, so for u, I'm integrating with respect to u. So I get this. I forgot my d theta. It should be in there. I go back, sine squared. I'm plugging in. So plug in, square this stuff. Simplifies, well, it simplified down to 1. I didn't write that, but it simplified down to 1. So when you integrate it, it's theta. And then it would be 2 pi. All right, so that's our first spherical one. Let's try one slightly more challenging here. This is the same thing as before. They switched the order around a little bit here, but it's already set up for you, so you're just integrating. And here we're doing 28. So 28, they just changed the order around, but it's already set up for you, so you're just integrating it. So practice this one by yourself. Pause the video and try it yourself. All right, my answer's on the next page, so hold on. Hold on, I'll tell you what it is. Oh, geez, it's complicated. Okay, it is 28 pi times the square root of 3 over 9. If that's not what you got, I'm fixing to show you my work. All right. Here's my work. I'll just let you look at it instead of talking you through all of it. But I will show you one thing in the second on the next page. So my daughter and her friend, those were not both my daughters in case you're wondering. I just have one daughter. That was my daughter and her friend Shannon. Not the friend that super glued her fingers together. That was her friend Briley with the super glue from my other video. You didn't get to see her, but that is Aaliyah's friend, Shannon. Aaliyah is my daughter. Shannon is her friend. Okay, so here's the part I wanted to show you. Notice here you have cosecant cubed. And so what I did to cancel, to simplify, I have sine, which was 1 over, it is 1 over cosecant. And so if you rewrite sine as 1 over cosecant, and then here you have a cosecant cubed, you can cancel and it gets it down to cosecant squared, which you can integrate. You weren't going to be able to integrate it like that. So that's a little trick in case you didn't get that part. That makes it easier to integrate because cosecant squared you can integrate and it's negative cotangent. Okay. All right, so that's kind of messy with some fractions. I'll leave it there for just a second so you can look at it in case this crazy answer is not what you got. Okay, let's see what's next. This is a long section because there's, in the old book, this was 2 separate sections, I think. Cylindrical and spherical were 2 separate sections. Here they're together. Okay, here's the directions. There we go. So 33 to 38, part A, find the spherical coordinates limits. That doesn't sound right. Find the spherical coordinate limits, that sounds better, for the integral, and then evaluate the integral. So you're trying to find volume. If you're trying to find volume with the triple integral, the function has to be a 1. So your function should be a 1. We're going to look at 38. So here's the picture. I don't know if you can tell from the picture, and I wish I could think of something to describe it. But on the outside, you have a sphere. Okay, it looks like a cylinder, but it's a sphere. But then on the inside, you have a cone. So I don't know if you can tell, but they've like cut out a section of that. So there's like a cone in there inside. All right, so my picture's not very good, but this is my picture. All right, so looking at the cone, notice that the cone, see the theta, not the theta, the phi is how far you fall from the z-axis. So because this is hollow inside, your cone was pi over 3. So you fall in pi over 3 before you even start. And then you start there, and then you fall the rest of the way to pi over 2. So that's where I'm getting those bounds. The cone starts at pi over 3, and then it goes down to the xy plane, which is pi over 2. So that's where you get the bounds for the phi. And then the rho, that was the radius of the sphere. Sphere radius 2, so it's between 0 and 2. And then because it goes all the way around, remember theta is the one that goes around. It goes all the way around, so it's 0 to 2 pi. So that would be my bounds. That's part A. And then for my volume, I put my bounds on there. 1, because for volume triple integrals, your function has to be 1. Make sure you have the extra piece, because in spherical, you've got to have this extra piece. And then d rho, d phi, d theta. All right, so we're going to integrate this. Integrating with respect to rho first. Plug in, simplify. Integrate with respect to, oh, just kidding, next page. Integrate with respect to phi, plug in, simplify, integrate with respect to theta, plug in, simplify. All right, let's see what's next. 44. find the volumes of the solids. So same thing. We're going to do 44. Their picture again is better than mine. Notice on the top, it's an upside down cone. And on the bottom is a sphere. All right, so try this one by yourself. See if you can, I'm not going to show it to you yet because you can see my work when I show you my picture. See if you can set this one up by yourself. It's just like the one we were just doing, except instead of separating it out into part A and part B, it's just all one thing. All right, so if you didn't already, pause the video, try it by yourself. Okay, let's look at it. I'm tired, sorry. And I have to get up super early in the morning to take my son to the airport because he's leaving for Arizona tomorrow and I'm super sad. So if there's tear stains on my papers and my videos, you'll know why. Okay, so here's my picture. All right, so here's the bounds for the cylindrical. Why did I choose cylindrical? Oh, because I had these Z's. All right, I was wondering why I didn't do spherical because it's a cone and a sphere, but I see now because I have the way the Z's are defined. So it was just easier to use cylindrical because it was Z's. I guess I should have told you that before I had to try it by yourself because you're probably thinking spherical. Anyway, here's the Z's. The Z, moves obviously bottom to top, and so in the region in the bottom is the sphere, and in the top is the cone. So this one is the sphere, this one is the cone. So I've got bottom is the sphere, top is the cone. The R, this is the sphere is of radius 1, so it's 0 to 1, and then it goes all the way around, so 0 to 2 pi. All right, so set it up in cylindrical. The extra piece is the R, but notice the function is a 1. The function's a 1 because this is volume. So I integrate with respect to Z first. Plug in, simplify. Here I'm distributing. And then notice this piece is going to require U substitution. I don't know if you can see that. Shush, my battery's about to die. It's warning me. I don't know if that shows up on the video or not. It's 20%. We are totally good. No worries. I have made videos on far less than 20% battery. Anyway, here, the last piece is going to need a U substitution. So I separated it out into two separate integrals because here I'm going to do the U substitution and here I'm not. So for this piece, here's my U substitution. And so I did them separately. So I'm working them down, this piece without the U substitution, this piece with the U substitution. So it works down so far to this. Turn the page. Your answer should have been pi. Sorry, I guess I should have told you that sooner. And there's the rest of the work. So if pi is not what you got, hopefully you can see the rest of this work. All right. These next two are out of order. But I'm going to do it this way because it's still on cylindrical. And then we'll do spherical next so they don't go in order in terms of numbers if that bothers you. Sorry there. I was trying to keep the types together. Okay, it's 54. Find the volume of the region bounded below by the paraboloid, laterally, which means on the sides, by the cylinder, and above by the paraboloid. So two paraboloids in a cylinder. All right, so I've got all that stuff here. So the above and below, that's the bounds on the Z because the Z moves bottom to top. So this is what's below, this is what's above. Oh, wait, first I got to change it to cylindrical. I already did that, but I forgot to mention it. This is in rectangular. You have to change it to cylindrical. So all these x squared plus y squareds become r squared. So this is it in cylindrical. So below and above in cylindrical. And then the r, if r squared is 1, then r is 1, obviously. And then it's going to go all the way around. So 0 to 2 pi. So you have for your extra piece the r. So this would be the setup. This one's a super easy one. Integrate with respect to z first. Plug in, simplify, r, plug in, simplify, theta, plug in and simplify. All right, so that one is my cylindrical example of those. Now let's look at the last one, which is spherical. This is number 50, so we're going backwards. But here it says, find the volume of the region cut from the solid sphere, rho less than or equal to a, just a number. So just some number a, by the half planes theta equals 0 and theta equals pi over 6 in the first octant. Okay, so I didn't draw the picture here because that's hard to draw. But these are two planes, okay? And then you're in the first octant, and this is a sphere. So your rho would be between 0 and a because it's a solid sphere. I'm in the first octant. So if I'm in the first octant, then I cannot fall past the xy plane. So I have to fall from the positive z-axis to the xy plane, which would be 0 to pi over 2. Because remember, pi over 2 is the xy plane. That's for my phi. And then for my theta, it's between those two planes, so 0 to pi over 6. So if you want to pause this and try the rest of it yourself, you can. All right, so make sure you got this extra piece. This is volume, so I have a 1 for my function. This is my extra piece that I get when I switch my dV over. And then here's my bounds. A is just a constant though, so when I integrate and plug in, I'm just treating the A like a number. So now when I do d phi, or integrate with respect to phi, that A is just hanging out like a constant. And then I'm going to simplify, and then I'm going to integrate with respect to theta. And I have A cubed pi over 18. All right, so that is all from 14.7. Make sure to memorize these new formulas for spherical. The easiest way to memorize formulas is to write them down several times. So don't forget also, these are extreme. These are probably not as important as these. These are really important, knowing what these extra pieces are, because you don't do a whole lot of switching from rectangular to spherical. So this stuff down here is what's really essential. All right, that's it for 14.7 and for chapter 14. So if you have any questions, send me an email.